My name is Spencer Scott. I'm a rising senior at Harvard studying astrophysics and physics with a minor in math. I spent this summer at the University of Florida in the SURF program working with Professor Deshika Narayanan and Dr. George Provon in the Astronomy department on the recovery of dust temperature distributions in galaxies from infrared SED fitting.
So now to talk about my research for this summer. First, what am I doing? What I'm trying to find out is how well do SED measurements recover the true dust temperature of galaxies. So how to do that, I'm going to look at the SEDs generated from simulations and compare the derived properties from using observing techniques to the true dust properties that we know from the simulations. And what we really want to know is how would these SEDs look when they're observed by telescopes that we have, such as Herschel or ALMA? What results do we obtain, and do they really align with the predictions from the simulations? So first, what is an SED? An SED stands for spectral energy distribution. Anything that has a temperature emits light at all wavelengths. In the ideal case, this is described by the Planck distribution for a black body. In a more realistic case, and what we do in this project, the data are described by a modified black body to account for the emissivity. So the first step to take is to look at the temperature from the SED peak. We get the simplest estimate of temperature from Wien's law, which describes the temperature of a black body according to where the peak in its emission is. However, this SED peak is extremely warm for dust. The dust temperature at this redshift is typically around 25 Kelvin. So now looking at the SED as well as the histogram of the dust grain temperature, we see that there's a lot of low temperature dust, but the SED peak is dominated by high temperature dust. So when you compare the dust temperature from the peak of the black body to the dust temperature from the simulations, you find that there's really no correlation between the mass-weighted dust temperature and the temperature from the SED peak. This becomes an issue. So the first step in looking at this is, well, maybe the mass-weighted temperature is not what's being picked up by the SED peak, and maybe it's a volume-weighted temperature. But because mass and volume weighted are qualitatively correlated, the Wien temperature and the volume temperature should not be correlated. So then, the next step is to try approximating an SED as a sum of black bodies. Because each grain of dust has its own temperature and will therefore emit its own black body radiation, it makes sense to estimate the SED that would be generated by the entire galaxy's worth of dust by the sum of a series of black bodies. So we will generate synthetic SEDs, not based on the simulations, but instead based on dust temperatures drawn from various distribution shapes and seeing which distributions match the SED as well as what the distribution shape should be. The first step in doing this is to see how the black body temperature is affected by just simply adding two black bodies together. So as you can see, the low temperature peak gets drowned out as expected. Looking at temperature distributions for the dust, it seems that a log normal distribution makes the most sense. The distribution shapes don't exactly match, but it's good enough for a proof of concept for now. So here you can see an SED that is generated from the sum of a series of black bodies with a mean of 22 Kelvin and beta equals 1.8, where beta describes the slope of the tail of the black body. The black points that you see are synthetic measurements made based on a 10% error bar. This is so that we can conduct an MCMC sampling of the posterior distribution. However, the curve fitting here only uses a single temperature to fit a distribution that is actually made up of a series of black bodies that are summed together. As you can see, when you do this, you get a temperature that is much higher than the actual mean temperature of the distribution. When you hold beta constant and instead of fitting it as well, you get closer to the real temperature, but you're still not accurately recovering the true properties of the dust. This situation as a sum of black bodies with temperatures that are drawn from a distribution, it's not natural to try to fit each parameter to a parameter of the distribution and see if you can recover the true input distribution. As you can see from the inputs and outputs, you are able to pretty accurately recover the properties of the input distribution of temperatures. So now moving back to the simulations. We wanted to see if we could recover the mean temperature of the distribution of the dust from each simulation. As you can see from the histogram on the right, qualitatively, the distribution shape doesn't exactly match. However, when you look at the outputs, the powder day mass weighted mean is 21 Kelvin, while the MCMC sampling recovers a mean temperature of 20 Kelvin. This is promising, as now we're recovering a distribution shape that has an accurate mean from the simulations. So the question now becomes, what distribution shape should be fit? Well, if you look on the left, you can see a histogram of dust temperature distributions throughout time. The bluer the histogram, the further back in time you go. You can see the histogram evolves and the shape changes over time. It eventually settles down into what looks to be a log normal type distribution. Part of the evolution of the histogram on the left can be attributed to accounting for the temperature of the CMB. The CMB is the cosmic microwave background. No dust can be colder than the cosmic microwave background. So when you look at the histogram on the right, the simulations in this case did not account for the CMB. You see much less of the same evolution and much less of the evolution and much more of the distributions settling and appearing to be the same roughly log normal shape. However, not accounting for the CMB is not physically correct, and so we need to make our model match the histograms on the left rather than the histograms on the right. Work on this project is ongoing. I'm currently trying to account for the CMB in my curve fitting parameters. This should fix the distribution shape issue. I'm also working on writing this up in a paper.
I plan on continuing to work on this project and hopefully publishing a paper along with a Python module to implement the curve fitting techniques I've worked on this summer. I'll be applying to the UF PhD program in astronomy for fall 2019 and hope to continue with a career in research. I'd like to thank George and Deshika for their guidance throughout the summer, as well as the University of Florida and the Provost for funding CERF. Thank you.